A very warm welcome to the NCERT series of Vyas Edification. As we undertake this chapter of Haloalkanes and Haloarenes, you would find that not just are we solving the plain NCERT questions, we are also giving you very useful insights about basic deep concepts. Conceptual gaps will be filled, and we would try to convey to the level best possible a very wholesome, holistic solution to the questions presented in NCERT. So there we begin. Name the following halides according to the IUPAC system and classify them as alkyl, allyl, benzyl, primary, secondary, tertiary, vinyl or aryl halides. Oh, very interesting. Now, how do you classify them? I'll just quickly revise the theory for you. Primary, secondary or tertiary means that they are attached. The halides are attached to primary carbon, secondary carbon or tertiary carbon. Which carbon is primary carbon? A carbon atom which is attached to only one other carbon atom, other than itself, only one carbon atom, that is called primary carbon. If apart from itself that carbon is attached to two other carbon atoms, then it is called secondary. Three other carbon atoms, tertiary carbon atom. Hydrogens attached to such carbon atoms are called primary, secondary or tertiary hydrogens, and halides attached to such carbons are also called primary, secondary or tertiary halides. Like, if you just take a look at this one, the very first one, what do we have? We have CH3 whole twice, CH, CH, CH3 and Cl. This is number one. Can you see that this chlorine is attached to this carbon and this carbon is attached to 1 and 2 other carbon atoms? This is a secondary carbon atom, so chloride also is a secondary chloride. And if you have doubts about this, look at this bond line notation. We have drawn the bond line notation. This carbon is attached to this and this two other carbon atoms. So this is a secondary halide. Yes, indeed. What about the second one? Let's take a look. We have this. Don't be confused by the C2H5. No. This Cl is attached to this CH, and this CH is attached to, well, 1 and 2 other carbon atoms. This is one carbon and this is second carbon, which are directly attached to this carbon. No, we are confused. I'll draw it full for you. CH3, CH2, CH. CH3, CH2, CH. Then we have CH3 on one side, and then we have CH, and then we have Cl, and we also have C2H5 in bracket, which comes on this side. Oh wow, this is the carbon we are talking about? Yes, this is the carbon we are talking about, and this happens to be 1 and 2. Two carbon atoms attached to our target carbon atom. Yes, so this is also secondary carbon atom. Yes, indeed. Actually, a hint is, if I have CH, this typically CH represents secondary. Yes, it does, provided there are no double or triple bonds. Indeed. What about this one? Instead of chloride, now I have an iodide, and this is CH2I. CH2 group is classical primary. Indeed, it is primary. I mean, it is just CH2I, like this. Clear cut case of a primary halide. What about the last one? No, the fourth one? It is, now this Br is attached to not C6H5 but CH. Wow, it is CH. CH means secondary. Yeah, but let's see, there might be slight variation. Let's take a look. There is some special advantage to this CH. I'll just draw fourth up here. This is CH3 whole thrice C. CH3 whole thrice CH3 whole thrice C. Fine. And then we have CH2 CH. I have CH2, CH, and then I have C6H5. Oh wow, I have C6H5 like this, and then I have a Br here. Fascinating. Since this Br is attached to CH, is this secondary? Yes, it is secondary. At the same time, it is not just only secondary, there is a special status attached to that. And what is that? If you have a carbon which is just adjacent to, what? I'm saying something very important, listen with great care. If you have carbon atom which is just adjacent to a benzene ring, this carbon is called benzylic. This carbon is called benzylic. So this halogen also is called benzylic halide. and it was mentioned, right? It is benzylic, yes indeed. So this is secondary and benzyl. So fourth is not just secondary, it is at the same time benzylic. Can it be secondary and benzylic together? It very well can be, yes indeed. Fifth, well, we have CH3, CH, CH3, CH, Br, CH3. Again, you notice that notorious CH and there is no benzene around. It has to be secondary. It has to be secondary. It is secondary, very much secondary. If you are confused, let me draw CH3, CH, CH3. Then CH, Br and CH3. This is the way the bond line notation is. And if you notice this Br, this carbon is secondary. It's very much secondary. And we now are discovering the trick also. CH2Br, classical primary, yes it is. I'll just draw the bond line notation in case you're interested. CH3, carbon is C2H5 hold twice, C2H5 hold twice, CH2Br. So this carbon is primary because it is attached to only one more carbon atom. Yes indeed, it is primary. So if I have CH2X, it is primary. If I have something then CHX, it is secondary. And if there is no hydrogen attached to that carbon is only one halogen and then alkyl, whatever, then it should be tertiary. Yes, indeed. Oh my God, there are more. Yes, there are more. What did you think, that we would not have any tertiary or something? Let's take a look. Now, I have CH3, CCl, C2H5, CH2, CH3. Now, this Cl is attached to a carbon which has no hydrogens. So, this is very likely tertiary. Yes. And if you are confused, let me draw the bond line notation for you. Seventh one I will draw on top. CH3, C. Then I have Cl, yes. Then I have C2H5. And then I have CH2, CH3, like this. Classic. This carbon is attached to 1, 2 and 3 other carbon atoms. This is a tertiary carbon, yes. And the halogen attached to tertiary carbon is a tertiary halide. Yes, very much indeed, it is a tertiary halide. What about eighth one? Let's take a look. You have CH3, CH, double bond, C. CH3, CH, double bond, C. Oh my God, then you have Cl, then you have CH2, CH, CH3, CH3, like this. Oh wow, now this is a carbon which is attached to 2 other carbon atoms. So can I say this is secondary? No, no, no. If that carbon has a double bond, then it is called vinylic carbon. Both these carbons, which are vinylic, this is a new term, I am confused. I'm just saying it again for you, don't worry, don't jump up so much. Hai na? Both these carbons, they are called vinylic carbons. Hydrogens attached to these carbons are vinylic hydrogens, and halides attached are called vinyl halides. Vinyl. This is a vinyl halide. Which one? And vinyls are not classified as primary, secondary or tertiary. Primary, secondary and tertiary is reserved only for sp3 hybrid carbon. The moment you have C double bond C, etc., then you no longer call it primary, secondary or tertiary. Is that fine? Fine. What about allyl alone? They'll come, don't worry. Let us take a look at this, ninth one. CH3, CH, double bond CH, then I have something else. Oh my God. Let me draw ninth for you. It is CH3, CH, double bond CH, then you have carbon, then you have a Br, and then you have CH3 and CH3. Oh wow, like this? Yes. Now this looks like tertiary. It very much is tertiary. But there is some additional angle to it. Actually, it is tertiary, yes indeed, but not just tertiary. Just see. This is tertiary, yes. Also, if you see, these carbons they are vinylic. Vinylic carbon, like this, right? And the immediate neighbors of vinylic are called allylic. What? It's a new term? Yes, it's a new term. So, immediate neighbors are this. So, this carbon is allylic carbon, and this carbon also is allylic carbon. Whenever there is a double bond, the carbon atoms which are forming the double bond are vinylic, and their immediate neighbors their immediate neighboring carbon atoms are allylic carbons. Beautiful. So this is tertiary, you said? Yes. But this is allylic, you are saying? Yes. What is this? Tertiary or allylic? It is both. It is tertiary as well as allylic. Wow. Like benzylic and something. Yes, this is tertiary plus allylic. Okay, that's nice. That's very nice indeed. Do we have more things? Of course, we have more. We have 10th, 11th and 12th. We have para-chloro C6H4 CH2 CH CH3 hold twice. Oh my God, what is that? Let us take a look. What is that? We need some clean space. I'll just erase a few solutions so that we have that clean space. So I'm drawing 10th here. It is, let me start with this. We have CH2, CH, CH3 hold twice. And then I have C6H4. This is C6H4 and para-Cl. Oh my God, this is para position. Exactly opposite is para position. So I have para-chloro, blah, 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 whatever. Which kind of halide it is? Now, since halogen is directly attached to an aromatic ring, it is an aryl halide. Wow. So, this is aryl? Yes, this is aryl. Right? So, whenever a halide is attached to the aromatic ring, it is called an aryl halide. Okay. What about 11th? Metachloro, now you have CH2. Fine. And C6H4. Okay. So, I have this. And I have apparently CH2, Cl. So, I have Cl, I have CH2, I have C6H4, that much I have drawn. On meta position, I have CH2. On meta position, I have CH2. Then I have carbon. Then I have CH3, CH3, CH3 like this. Oh wow, this is the compound? Yes, this is the compound. 11th. And which location is this? Neighboring to benzene ring. Please note, 6 carbons on benzene ring are all phenylic carbons or aryl groups, you can say. And this is benzylic. And this is primary because it is attached to only one other carbon atom. It is primary and benzylic. So, what is 11th? It is primary and benzylic. Fascinating. And the last one, orthobromo C6H4, my, what is this? Let us start making it. Well, let me make a benzene ring. And then they say orthobromo. So, on ortho position, I have drawn bromo, I have drawn C6H4. This is C6H4 because 2 hydrogens are taken away. Now, I have CH, this is C. I have then methyl, I have CH2, CH3 like this. Okay. But this halogen is attached directly to benzene ring. Is it primary, secondary or tertiary? No, in such cases we don't say primary, secondary or tertiary. We simply say that this is aryl halide. Wow. So 12th is aryl? Yes, 12th is aryl halide. Give the IUPAC names of the following compounds. We have compounds and we are supposed to supply the IUPAC names. First, CH3, CH, Cl, CH, Br, CH3. Let us first draw the structure. Let me draw it here. CH3, CH, Cl. Then we have CH, Br and we have CH3. What a beautiful molecule. First of all, as per the nomenclature rules, I am supposed to first draw, yes, the longest carbon chain. This is the longest carbon chain. Then I have to number. Numbering has to begin from whichever side gives you first substitution. This is 1, 2, this is 1, 2. From both the sides we get substitutions on the second carbon. Then that rule is useless. Now we come to the next rule, which is alphabetical. Alphabetically, bromo comes before then chloro. So 1, 2, 3, 4. This is how we will number. And what would be the name? It is 2 bromo, 3 chloro, butane. Oh wow. That's it? That's it. It is a vicinal dihalide. Vicinal dihalide means that just adjacent atoms have one halogen atom each. The second one, let's take a look. This is CHF2 CBrClF. Let's draw it once. What do we have? We have two carbons. We have CHF2, so we have two fluorines like this, and then we have C, which has Br, which has Cl, which has F. My God! So you have just started putting so many halogens here. Which carbon would be labeled as carbon number 1? Tell me. Well, it has two substituents and this one has three. So first of all, number of substituents you have to see. Whichever has greater number of substituents is preferred, and only when that number is same we talk about alphabetical order. So this carbon is 1 because it has 3 substituents and this carbon is 2. What next? Well, we have 1 bromo, 1 chloro, 1, 2, 2 trifluoroethane. Fascinating. This is the name? Yes, this is the name. And now the third part, it says Cl, CH2, C, CH2. This is carbon chain. How many carbons? 1, 2, 3, 4. 1, 2, 3, 4. And I have a Cl here and I have a Br here. Right? This is the way it is. How do I name it? Again, simple enough. 1, 2, 3, 4. Why not opposite? Alphabetical order. Bromo comes before chloro, otherwise it is symmetric. So what will be the name? It is 1 bromo 4 chloro but 2 ine. It is 2-butyne, please note. Right? This is third one. What is the fourth one? Oh my God. You have CCl3 whole thrice CCl. CCl and you have CCl3. You have CCl3. You have CCl3. How do you name this? How do you name the CCl3? CCl3 is trichloromethyl. And there are not one but 3 groups of this kind. So what would be the appropriate name? Well, let's first make some space for this and then we'll try that out. How do you write that? Just give me a sec. Very beautiful name. Parent chain is only one carbon. So this is methane, chloromethane. So this is chloro. Why? Because of one Cl. And then you have 3 groups. Chloro. Then I will have tris. Why tris? I will just tell you shortly. This is trichloromethyl methane. Oh my God, that's very dangerous. That is not at all dangerous. See, you have 3 groups like this. So please don't count this and this as main carbon chain of ethane. No. CCl3 groups, 3 groups are already present. Because there are 3, I will use tri. But the name itself, again within the brackets also I am using tri. It is trichloromethyl. If it is trichloromethyl, then within the brackets if I am using ditrite, etc., then outside I should use bis, tris, tetrakis, pentakis, prefixes of numericals like this. So this is chloro, tris, trichloromethyl methane. Wonderful name. This one, 4th. Done all these. Let's take a look at 5th one. It says CH3C, there's some dirt, then CH. So I have 1 carbon, 2 carbons, 3 carbon and 4 carbon. So first let me draw butane like this. Okay. Methyl is fine. I have CHBr. So the CHBr, fine. Then I have some parachlorophenyl. Okay. So let me make a phenyl and parachlorophenyl. Okay. And then we have methyl. Yeah. This is the dirty molecule. Oh my God. And what would be the parent chain? Well, I think the parent chain is the way it is indicated. This is the best parent chain. Why don't you take benzene ring? If I take this as parent chain, it has a side chain, then side chain again has a side chain. That also is bad enough. We could write it both the ways actually. Let me try it out this way. This would be 1, 2, 3, 4. Why this side? Why not the opposite? Alphabetical. The reason is. So the name is 2-bromo. I'm solving fifth. It is 2-bromo 3. What is, 3? Is it phenyl? Yes, it's phenyl. But this is 3 para chloro. If you don't want to use the word para, you could use a number also. And what would be that number? It would be 1 dash, 2 dash, 3 dash, 4 dash. If you are numbering on side chain, use dashes, and whichever carbon is attached to the main chain, that carbon is given 1 dash. Right? So it is 4-chloro. Why not dash? Within brackets, you don't have to apply dash. So 2-bromo 3, 4-chloro phenyl or parachlorophenyl, both are okay, butane. So side chain has a branch? Yeah, it has. Why not the other way around? I also could have chosen another main chain as well. Like, see, please remember, IUPAC has made a very clear recommendation. What is that? That a given molecule may have more than one correct IUPAC names. But every name must represent a unique compound. So, can it have one more name? Possibly. Let me just show it to you. What about this? If I choose this as main chain, what would happen? Let's take a look and see what would happen. Had this been main chain, well, numbering would have been either 1, 2, 3, 4 or 1, 2, 3, 4, something like that. What would be the name? This is chloro simply. And what would be this? This would be, I think, 1 dash, 2 dash, 3 dash. Okay. So it's 2-bromo 1-methyl propyl, something like that. More complicated name. Just for the sake of practice, let us name it like this, and then we'll discover whether it's correct or not. So if benzene is the parent chain, 1, 2, 3, 4. This is the way we should number it. Why? This is chloro and this would be bromo. So bromo alphabetically comes first. So we have 1 on number 1. Which group I have? This is side chain. So 2-bromo 1-methyl propyl. Oh my God, this would become the side chain, such a huge 131. And then I have 4-chloro benzene. In case I choose to name it the other way around, it is this. Which is more complicated, this or this? This is more complicated. And IUPAC always has favored more simple names. So a better solution is this, yes, and this is a more appropriate IUPAC name. Still, why did you solve this? Just to give you a revision and quick idea about, in case you have side chains which are further branched, how do you name them? Just to demonstrate those rules, I have solved this in this fashion. This is not a strong solution. This is the better name and more appropriate name. If you just want one name, stick to this one. Done? And the last, let's take a look. Let us CH3 whole thrice C. Well, I have tertiary butyl group. And then I have CH double bond C. CH double bond C. And then I have Cl. And then I have benzene ring. And on para, I have iodine like this. Para iodine, they have indicated. Not too ugly, not too pleasant either. Let's see, how do we name this? First of all, you have to choose the parent chain. And the parent chain is apparently this one. 1, 2, 3, 4. That's it. That's it. This is butene. Yes, it's butene. So I have 1-chloro. Yes. And this is A, B, C, D, E, F, G, H, I. Then iodophenyl and methyl. So I'll name it as 1-chloro. Fine. And then this is 1,4-iodophenyl. Yes, very much. This is 1 dash, 2 dash, 3 dash, 4 dash. That is why 4-iodophenyl. And now you have 3,3-dimethyl. I don't have space yet, I'll come back here. 3, 3, sorry. It looks a little ugly, but it's not. Let me use a darker color. 3, 3, dimethyl, and 1, 2, 3, 4. 4 carbons. So but-1-ene. It's but-1-ene? Yes, it's but-1-ene. Don't you forget this alkene here, right? This is the way we would name the sixth one. These are the IUPAC names. Write the structures of the following halogen compounds. Lovely. Let's take a look. The first one says 2-chloro-3-methyl pentane. So first let me draw pentane. This is pentane. 2-chloro-3-methyl pentane. Wow, is this the structure? Yes, that's it. Beautiful. Then second one is para-bromo-chlorobenzene. Well, this is the first one. Second I could draw here. Para-bromo-chlorobenzene. This benzene, chlorobenzene is this much, and on para position I have bromo. This is para-bromo-chlorobenzene. That is awfully simple. Third one, we have cyclohexane. This is third one. Let's take cyclohexane. I have 1-chloro and 4-ethyl. 1, 2, 3, 4. 1-chloro, 4-ethyl cyclohexane. This is the third one. Fourth, I have octane. The parent chain octane. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. 1-iodo. So, well, so let me draw 1-iodo. And I have 2. On second carbon we have phenyl. On second carbon we have phenyl. And it is not just phenyl. Phenyl has 2-chloro also. That means this is 1 dash, 2 dash. So, this is 2-chlorophenyl. That's it. That's it, my dear. This is the fourth one for you. Fifth, 2-bromobutane. That's simple. This is 2-bromobutane for you. Very lovely. And the sixth one, 4-tertiary butyl. Okay. 4-tertiary butyl. First of all, we need a heptane. 1, 2, 3, 4, 5, 6, 7. We have a heptane. And then they say, let's take tertiary butyl on 4. 1, 2, 3, 4. On fourth, I am taking a tertiary butyl. Fine. On third, I am taking iodo. That's it. That's it. That's simple. This is sixth question for you. Seventh, 1-bromo, 4-secondary butyl. Let's look at the parent chain, benzene. Benzene is the parent chain, yes. On this one, I have 1-bromo. I have 1-bromo. 4-secondary butyl. On fourth location, I don't have much space down there, so I'll just change this bromo location. First, just let me say this is 4. I'll just make secondary butyl here. This is a secondary butyl group. If this is 4, this becomes 1. I have bromo here. And I have 2-methyl. I have 2-methyl. Lovely. Right? This is how I draw it. This is 7th. And what about 8th? 1,4-dibromobutene. This is butene. 1,4-dibromo. It can't get lovelier. Like this. This is my 8th compound, and there we are. Which one of the following has highest dipole moment? And we have CH2Cl2, CHCl3 and CCl4. Now please note, CCl4 is such a beautiful tetrahedral and symmetric molecule. All the dipole moments would cancel and it would have a zero dipole moment, definitely, yes. What about chloroform? Chloroform would have C, H, and then I have Cl. I again have a Cl. I again have a Cl like this. So these three Cl, 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 their vectors add up, and I have, they are withdrawing in this direction like this, like this, like this, right? So I have C, H, and all these three vectors, one is this side, and that side in tetrahedral. So net vector adds up in this direction. This also. So well, I get something like this when they add up. What about this one? I have C, H2, and I have Cl2. These two chlorines, right, they would again vectorially add up in this direction. And these hydrogens also would add up in this direction. So honestly, this is very clear. You get mu 0, this one and this one. It could have been just anything. If you give me the liberty of just adding one more, why don't we take CH3, Cl also? They show a very beautiful trend. If I just add C, H, H, H and Cl here, the actual order is this. Most or the highest dipole moment is possessed by methyl chloride, CH3Cl. Now, if you have just one Cl, it is withdrawing from CH3 very beautifully. If already one Cl is there, the second Cl cannot withdraw as much. And three Cls again together will withdraw significantly, but again they will also vectorially, one component of these Cls will cancel also. Only one component would add up. So ultimately the order is this. You have methyl chloride, which is not there in the question, highest. CH2Cl2 is still more than chloroform, and CCl4 is the worst. Why? Because as Cl groups add up, they vectorially keep on reducing or subtracting the component of the dipole moment, simply because dipole moment is a vector quantity, and when you vectorially add, see, in this case horizontal components will cancel, only the small vertical component will add. This is the reason why you find the dipole moment decreases on increasing the number of Cl atoms. A hydrocarbon C5H10 does not react with chlorine in dark. What does that mean? Please note, this C5H10 is formula CnH2n. So there are two possibilities. It could be an alkene, or it also could have been a cycloalkane. You can think of two possibilities. It could have been an alkene, or it also could have been a cycloalkane. Yes. Which one? Now they are giving you a hint. It does not react with chlorine in dark. What does it mean? It means now chlorine, all the halogens, chlorine, bromine also for that matter, it can add on alkenes in dark. So if it is an alkene, it would react in dark, but because it does not react, that means it is not an alkene. It has to be a cycloalkane. But gives a single monochloro compound in bright sunlight, photochemical halogenation. Now, honestly, it could have been this. I also could have had more weird, possibilities like this. I'm not denying them. But it gives only single monochloro compound, and the moment I say single, all this is ruled out. If I have Cl2H nu, all these positions are equivalent in cyclopentane. I can, in whichever place, there are 1, 2, 3, 4, 5 carbon atoms. If I substitute Cl here or here or here or here or here, in every case, I would obtain the same compound, chlorocyclopentane. It is a single monochloro compound. This is the one. The hydrocarbon, Which is the hydrocarbon? The hydrocarbon must be cyclopentane. Write the isomers of compounds having formula C4H9Br. Wow. Now C4H9 is a classical butyl group, right? How do I write the isomers? Let me see how many butanes can I draw. I could have drawn simple normal butane or well, what you normally call as isobutane, something like that. Why you are drawing repeatedly? Just for fun. Now there are only two butanes. I have written the same thing twice, but again I have normal butane or isobutane. If I remove one hydrogen and I attach one Br, I could have done it here, yes. Even if I do it here, whether this side or that side, it would be one bromobutane. So there is, these two sides are identical, there is no difference. Similarly, these two sides are also identical. Why? If I just attach a Br here, it is 2 bromobutane. So I have 1 bromobutane and I have 2 bromobutane. Yes. Even if I put a Br here, say I happen to put a Br here, it is nothing new. It will be then counting from, will be from this side, not from this side. It would again be 2 bromobutane only, nothing new. So I just have two possibilities, 1 bromobutane and 2 bromobutane based on butane parent chain, right? What about isobutane? Let's see. Well, can you see that CH3, CH3 and CH3, these 3 carbons are identical in the sense whether I put a Br here or here or here, it's one and the same, Br or Cl, whatever it's here, Br. So if I have this and if I feel that this is different, no, this is not different, it is the same. And this is same as this. Why? Try naming them. If you have any confusions, just try to name them and you would discover that they are identical. The name would be, see, 1, 2, 3. What is this? This is 1 bromo, 2 methyl, propane. Same. 1, 2, 3. 1, 2, 3. 1 bromo, 2 methyl, propane. 1 bromo, 2 methyl, propane. They are same. Yes. So you don't have to count them separately. It would be very stupid to write them 3 times. But you wrote them 3 times just to explain you. Right? I need not write them 3 times. Please understand that these are equivalent positions. Okay. Do I have any other option? I do. I could put a bromine here. Oh wow. And this is 1, 2, 3. I get 2 bromo, 2 methyl, propane. Right? So there are 4 isomers like this. And if you want, I could write their common names also. Very popular and very useful. This is N-butyl bromide. They are common names nonetheless. This is secondary butyl bromide. And this is isobutyl bromide. And this would be tertiary butyl bromide. I have given you the structures, the method to construct them, the IUPAC names as well as the common names, everything. These are the possibilities. Write the isomers, I have written everything. This is it. Write the equations for the preparation of 1 iodobutane from tang tang tang. Well, 1 iodobutane from butanol. Now I have 1, 2, 3, 4. This is 1 butanol. And I want to convert this to 1, 2, 3, 1-iodobutane. What do you think I would need to do for this? Well, I also have 1-chlorobutane which I intend to convert to 1-iodobutane, and I have but-1-ene which I intend to convert to 1-iodobutane. How shall I do it? Well, let's take a look. Now when you look at question number 1, there are two very interesting roots. What is that? See, first of all, notice what exactly is happening. You are substituting OH by I. So it has to be a substitution, right? Not just that, I would be available as I plus or I minus, it would be available as I minus. So it seems like nucleophilic substitution. And this is primary carbon. Now, if you want primary to primary, it clearly indicates SN2 mechanism, and by SN2 mechanism, if I am doing a substitution, this is nucleophilic substitution, we are using nucleophile as I minus. So what could have been a possibility? One possibility could have been just use HI. What happens? There are two steps. You have alcohol plus HI. Please note, we should not have hot conditions, otherwise there would be a problem. Cold is good enough. And oh wow, what happens? H plus is donated here and I get OHH plus like this. Oh wow. Now please note OH minus. If OH minus is pushed out, OH minus is not a good leaving group. But now I have, first of all, I have free I minus. I minus is a great nucleophile, yes. And at the same time now H2O would be a good leaving group. So if there is an attack now, attack. This is a classic SN2 attack. And if this pushes out H2O, I would get what? I would get something like this. Oh wow, this is 1-iodobutane, yes. And I get H2O, yes, very much. Is it a good method? It's a beautiful method with one limitation. What? Although this might not be discussed in NCERT, but you should be aware that if you heat it and if this cation departs on its own without this attack, then there might be a component of SN1 mechanism as well. If you heat it, portion of SN1 will increase, there will be added complication of rearrangement which will be very unpleasant. So just make sure that you are using HI and this is conducted at low temperatures only, and you would get very happily 1-iodoethane. Could there be another method? Yes, I am giving you, this is a very simple common method, I am giving you that. In addition, I am also offering you a beautiful alternate method as well. This, my dear, is a method called acetylation. See, the problem is, approach it like this, we are converting, now this is a poor leaving group. And this poor leaving group has to be converted to a good leaving group. One method was use HI, add H plus, and you can do that. We saw that. I am giving you a second method. This is method 2. And this method 2 will have better yield and less drastic reagents. And this would be, treat this with ClCOCH3. What is this? This is acetyl chloride. Wow, what happens? You would find that once they react, this HCl goes away and you would have O, yeah, and this O gets attached to COCH3 like this. Now this is no longer OH, this is OCOCH3, and this entire group is now a good leaving group. Lg is leaving group. And now in the second step, you treat this with, in the first step you add this, in second step you add Ki. Oh wow, attack, classic SN2 attack. And this is pushed out. And what do you get? Well, you get CH3, COO minus, which is pushed out, and 1-iodobutane. I am giving you not one but two methods of this preparation. Now, starting with 1 chlorobutane, I have to prepare 1 iodobutane. 1, 2, 3, 4. 1 chloro, you're giving me 1 iodo. This is not at all difficult. Finkelstein's reaction. Ki in acetone. When you add this, you find that there would be substitution. KCl will simply precipitate out and you get all chloro or bromo halides can be converted to iodohalides by using Ki in acetone, the classic Finkelstein's reaction. Second is very easy. Is there a mechanism involved? It is not asked, but it is classic SN2 in case anybody is interested. And the third one is but1ene. Wow. I have from 1 butene, I am supposed to get 1 iodobutane. Now what happens if I add simply HBr or HI to this? If I just add HI, let me add HI and let me see what do I get. If you add HI, first you would get H added here, carbocation here, Markovnikov's rule, and you would have H and I like this. So you would get 2 iodobutane. If you simply add HI, you get 2 iodobutane, which is something which you don't want. Yes. So is it a good idea? It is not a good idea to add HI directly. Then what should I do? I need anti-Markovnikov addition. And anti-Markovnikov addition, is it crash? I mean, we call it crash, right? No, there is a scientist also called crash. Crash effect. You use first HBr and you use peroxide. So this would give you anti-Markovnikov addition. You get H here and Br here. 1 bromobutane. And now you use Finkelstein's reaction. Ki in acetone. In the second step. And Br changes to I. And you get a nice happy precipitate of KBr. Done, 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 done. Right? 2 steps like this. This would be an appropriate conversion. What are ambident nucleophiles? Explain with an example. The nucleophiles which can donate the lone pair in more than one ways are ambident nucleophiles. What is donate the lone pair in more than one ways? This way or that way? No, through one atom or the other atom. If they have more than one atoms through which lone pair may be donated, then they are termed, my dear, as ambident nucleophiles. Classic example is cyanide. Cyanide could possibly donate a lone pair through carbon. It also could have donated the lone pair through nitrogen. That is why cyanide is an example of an ambident nucleophile. I mean, if you want to be more specific, say something like this. If I have isopropyl bromide and I treat this with potassium cyanide, what happens? Well, the moment they are mixed, I get a cyanide like this and KBr. In this case, when cyanide is acting as a nucleophile, something lovely happens. It attacks like this, it pushes out bromide, and this is the way it behaves. Unfortunately, another drama is also possible. If I take same isopropyl bromide and I use silver cyanide. Now, Ag plus is a very funny molecule. Ion rather. Ag plus attracts carbon very beautifully. So the lone pair on carbon gets attracted to silver itself. Only nitrogen is free. And you find that when isopropyl bromide dissociates to isopropyl cation plus Br minus like this by SN1 mechanism. I repeat, you don't have to know mechanism, you don't have to write mechanism, it is not asked. But in case this happens, you would find that now this nitrogen can donate the lone pair, it can get itself attached, and you would get an isocyanide like this. Wow. And I get a precipitate, nice, happy, lovely precipitate of HBr. So with KCN and AgCN, I get different products. I get cyanide or isocyanide. same nucleophile cyanide is acting in two different ways. Why? Because it can behave as an ambident nucleophile. For those who are looking for a written ready-made answer, this is also a written ready-made answer. Well, take a look. And I'm just moving myself out so that you can take a screenshot and find it useful. Done? Done. Which compound in each of the following pairs would react faster in SN2 reaction with OH minus? 1 or 2? Well, let's take a look. You have CH3Br or CH3I. If you compare, both are both contain methyl, the difference being Br or I. The better leaving group would give you a faster SN2 reaction. So since I minus is a better leaving group Lg as compared to Br minus, the rate of reaction of CH3I will be more than the rate of reaction of CH3Br. Simple but elegant. What about this? I have tertiary butyl chloride and methyl chloride. I have CH3, Cl, and I have CH3, 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 Cl, like this. Now what happens in SN2 attack? There is a backside attack of OH minus. Just imagine OH minus is here, attacks, quick, this is primary. OH minus is here, attacks. Where to attack? This is so much of crowd. Yeah. You find that because of crowding, SN2 attack in tertiary is very, very, very poor as compared to primary. So the rate of reaction, the rate of SN2 reaction will be much, much more for methyl chloride than for tertiary butyl chloride. Always this is the case when you are comparing the rate of SN2 reaction.